Okay, the next type of memories that we will discuss is the serial access memory. This is as opposed to the random access memory. And serial access memory, basically, there is an implied order in which data is stored or read out. Basically, the access mechanism is guarded or sort of organized by certain order. We will talk about shift register, tap lines, and serial um, serial out, parallel in, serial out, part of the SERDES devices and the queues as well. Okay, so let's keep going here. Okay, so the shift register, which we covered in earlier courses, are just a collection of registers, like for example here, there are 8 of them. So you have the data comes in, and this data is 8-bit, and the queue of this data goes to the input of the next, and the queue of this data goes to the input of the next, and queue of this data goes to the input of the next, etc., etc. So in this case, this shift register has a depth of 4 cycles. And you can have it as many register levels as you wanted to. And in this case, we say that we have a 4-stage 8-bit shift register. And every clock cycle, the data moves one level to the right, obviously. And this is used quite a bit in DSP or signal processing applications, in which we would like to delay the data for certain applications, like filters, for instance. Okay, so very, very simple, nothing to be said there more than this, except that for these shifters, sometimes flip-flops are not the most efficient way of doing it. So what we do is that we kind of replace the flip-flops with a RAM. And we access the RAM. The RAM has 2 pointers that we can access. I'm sorry, it has 2 pointers. One, a read pointer, in which is used to get the data out of the RAM, and a write pointer, in which we write the data to the RAM. And those are the read and the write pointer. They are initialized to the first entry. The read is initialized to the first entry, for example, 000 in this case, and the write is initialized to the last entry, for example, 1111 in this case. Okay, and you can think of this more of a circular FIFO. For instance, you can think of this FIFO as circle, like so. Okay, so so let's say, for example, here, um, this is address 0, 1, 2, 3, 4, 5, 6, and 7. So for instance, if I have a data which is, let's say, suppose I pushed a data which is A, B, C, D, E, F, G, H, where really this is the earliest and this is the last. So you will see that this A is here, B is here, C, D, E, F, G, H, right? And then we'll start, if we have another data that comes in H, let's say I, so this I is going to come uh, and occupy right here, okay? And you will see that the H will pop out. Now, be careful that you will have a meaningful data comes out whenever you complete populating, meaning complete writing data to the circular fiber, and then the data will come out meaningful. But before you populate it, right, it will not. So you will need 7 cycles. So similarly here, in our shifter here, in the first 3 cycles, there is nothing meaningful is coming out until you fill those registers with meaningful data, and then you get meaningful data coming out. Okay, and before that you don't. And obviously, these fill cycles are typically ignored in the processing, or you assume they are zeros or some default value. Okay, so that's for in terms of implementing the shift register using RAM, because RAM is more efficient. Now, let me just say that you would want to do this for large shift registers. For instance, for four-level shift registers, I'm not sure this is really very efficient to use a RAM, because RAM comes with its luggage of problems and sensitivity, and you have to be careful. It has a controller, it has this and that and the other. So if you have a very small shifter, you wouldn't jump into using dual ported RAM. By the way, dual ported, it means that you can have two ports of data. One to it supports an address for data to be read, and another address for data to be write. So in one cycle, you can basically read out a data and write into a data, which is what we want to do in a shift register. Okay, so um, another type of shift register is the tapped delay line, and the tapped delay line is used to program a delay. Well, suppose for instance I want to have a delay for one cycle, two cycles, three cycles, four cycles, seven cycles of my choice. So what we do, we create this kind of a tap line, and if you look at this very simple structure, because it's repeated. Look at this is a shift register of one cycle, which means there is just one level of FIFO inside here, which is what we see here. And then the output of this get into a multiplexer, and the multiplexer has two inputs, one coming from the shifter and one is bypassing the shifter. And by activating this control signal, I either take the delayed cycle of one cycle or no delayed. Okay, so depends on the values of this 0 or 1. Similarly, if you look at the second stage here, right, again, I have a shift register of 2, which means I have two levels of registers there. I can delay the data for two cycles. And again, similarly, I have the input of this bypassing, and then it goes to a multiplexer, and then a control signal here. So basically, based on this value, I can delay the data 0 cycle or 2 cycles. Okay, and repeat. So SR for cycles, SR 8 cycles, SR 16 cycles, SR 32 cycles, and you can see that this is almost looking like, if I may use the eraser here, this is looking like as if I have a binary value. So suppose, for instance, I want to delay this data. Let's see, this data. I want to delay this data 3 cycles. So to delay 3 cycles, what do? I activate this. Whoops. Let's see if I chose the right pen. Here's my pen. I activate this control signal, and I activate this control signal and deactivate all this. So what happened is here is that when my data, the data will bypass this, and then goes and bypass this, and it doesn't wait. It doesn't wait. It doesn't wait, and then it comes here. Oh, it has to go through this because the control signal will pick. So 2 cycles delay, then it comes in here. Oh, it has to go here because the control signal is active. 1 cycle, 2 cycles apply. What's 1 cycle delay? It means I'm gonna delay this 3 cycles, 3 cycles, and you can see that this is 1 cycle, and here's 1 cycle. I'm gonna wait here 1 cycle, 2 cycle, that 3 cycles. Notice that the wait here, the delay here, the delay here. Um, the delay level here, I'm talking about this number here, equals 2 to the I, where I equals delay, the number here. Okay, so delay 5, 2 to 5, 32. Delay 4, 2 to the 4, 16. Delay 3. So this is almost like you are coding the delay in binary number. And this will, so in other words, if I want to delay 7, this is what I want. I activate the control signal like so: 0 0 0 1 1 1. That's the function of tap delay line. It is basically a programmable delay of stages. Okay, all right. So another one is that when you are supposed to convert the serial data to parallel or parallel to data. So suppose, for example, you are shifting in data to the shift register. Okay, and then you want to pull it out, right? And in parallel. Or the opposite, you load the data in this in parallel, then you shift it out serially. Why would you do that? Well, the obvious application is really when you are communicating between two systems. And obviously, the data in this system one, is in parallel. But when you communicate it, you would communicate it by bits, right? By bits. Why you want to do that? Because it's cheaper to to send out data by bits. Whether you will need a wire or you need to send it. So it's a lot better to send these symbols bits by bits. Okay, so to do that now, our words here, data need to be what? Need to be serialized, and this is exactly the circuit that we use. We take the whoops, sorry, that's not what we want to use this one to serialize. So we load the parallel data here and then we shift it out, so we serialize it. At the destination, I will use this circuit where I receive the data in serial, right? So I will clock this 4 times, then I pull the data at once, and that pulling of data will happen when I get the parallel data. Okay, so I will clock this 4 times, so I get these data and then read out the data in parallel. So this is the type of serialization, deserialization, and commercially some companies refer to these devices as SERDES. SERDES as serializer, deserializer. Okay, so this is a serializer. This is a deserializer, which is, I'm sorry, this one here. Okay, all right. So this is what we want. Okay, and then here what we have finally in terms of these these storages which has some kind of order to access the data, we get into finally the queues. The queues are very important hardware structures when we communicate with systems, in particular if those systems are asynchronous. And basically, typically you will have a producer of data sending data to a consumer of data, which consumes the data. And the producer could be a sensor, and the consumer could be a system which reads the sensor. And because the data rate between the two might vary, you want to have some kind of a buffer, here, which kind of absorbs this speed differences between producing and consuming data. In other words, you would want to have some kind of a reservation station where you keep things around just in case this guy is busy, the consumer, or the producer is not producing as much. So this is kind of a waiting station, this buffer. Okay, so this is the data. Let's look at this structure here, the queue. This is the right data coming from the consumer, which produces the data, the sensor, for example. And this is the clock, okay, that comes from the producer. And obviously, when the queue becomes full, I have to tell the producer, stop. I am now full. I have no more for data to be stored. Okay. Now, so and at the same time, you have this consumer which reads out the data and it provides its clock to the queue. Right. So notice that because we have two clocks, that indicates that the system which produces the data, writes the data, the system which reads the data, they work off two different clocks, and that's why they are, this is for asynchronous system. So we read out the data, and we keep reading out until we finish all the data. If it happens that we finish the data, we send an empty signal to the consumer, to the system that reads the data, and we say, stop. I no more have data for you. Okay, so you have these flags for empty. In advanced FIFO design, you have almost full indicator or flag and almost empty. And the reason is that some of these fast systems, to indicate the flag, you might have data which is in flight, and you do, because the system already sent out this data to be written. You want to send this indication very early, almost almost like throttle down. It's like you are saying to the producer, slow down, slow down. I'm turning on the orange light for the traffic light here. Slow down. I will turn red very soon, which is the full signal. Similarly for the empty and almost empty. Okay, so these are also flags that helps to throttle down the producer and consumer. Okay, now, so in terms of hardware, we call these queues FIFOs, because basically this is the queue. What comes in here first leaves first. So we say it is first in, first out. What we need here, we need really a read and a write pointers, and basically, typically they are implemented by memories. And when we reset the system, both pointers, the read pointers, are initialized to the first element in the memory. Okay, on write, we advance the write pointer. Now, if the write pointer about to catch the read pointer, okay, and about to catch, it's -1 or +1 based on how you organize your addresses, then the FIFO becomes full. On the read side, whenever we read, we advance the read pointer, and if it is about to catch if it catches the right pointer, then the FIFO is empty. Okay, so notice the about to catch and catch here. Okay, so about to catch, it's the plus minus for the addresses, +1 -1. But here for the read, if it catches the right pointer, 8, because they are initialized both to the same. So at reset, so they are initialized to the same address, meaning the FIFO is empty. Okay, so if the read pointer catches, it means it is now equal to write pointer, then the FIFO is empty. Now there is another structure that we use in hardware, which called a stack. It's used in programming, which is first in, last out. Okay, first or last in, first out. And those are stacks, and also it has a pointer to the top of the stack, and at the bottom there is a pointer that tells me at the bottom or the top of the stack. So at reset, I initialize this top of the stack pointer to the first element, which is basically right here. Okay, and on the right, the pointer is incremented. So on the right, the pointer goes up like so to the top of the to the limit of the stack on the top. Um, and so this is the top of the stack, and this is so kind of the where the limit of the stack is. Okay, and on the read, I send the pointer to the other direction towards where we started and reset. So the point, and on the right, the pointer is incremented. If it catches the last element, then this stack is full. So if we go all the way up to the right and we catch the last element, which is here, then the stack is full. On the read, the pointer is decremented, sent to the bottom, and if it reaches the first element, okay, then it's empty. So he's referring here to these elements, which is kind of, you will see different really notation, that this is the last element, this is the first element in the memory. So you will see different textbooks use different notation, but it is basically moving this top of the stack up and down, up on writes, down on reads. Okay, all right. So that's as much as we can say about the memories. Okay, and next what we will discuss is the third type of memory. So we have the random access memory, the um, uh, the random access memory, the memory, the serial memory, and the third type, which is content addressable memory. The content addressable memory is like any regular memory. Okay, let's just use a highlighter here. It's like any using any memory. It has a read command, a write command, an address. Okay, but it has a data, but it has an extra thing, which is a key. And this memory, it is able to search the key inside it. It searches for the key if it is inside its content. So let's say, for example, I have a memory. Okay, you know what? We'll take this example. Some of the application for this is the TLB, as you might have studied in the computer organization and computer architecture classes, and basically they convert the logic address into I'm sorry, the virtual address into physical address. And so and when the virtual address comes from the CPU, you would want to check if the TLB has the virtual page number. If you have it, then you get the physical page number so that you can form the physical address. So that hit. So that searching for virtual page number is why we need a CAM. So that's we hit a match, and this match is used to access this table of addresses. Okay, let's see how this match is happening. I have here a simple example, or I'm sorry, it's the simple matching circuit. And suppose, for instance, let's say, for example, let's see, so here what we have is that I have in this I have a memory, okay, a CAM memory. I don't want to, I want this black. Let's choose a red color here. Okay, yeah. So in my memory, suppose I have in my memory four words. Okay, four words. So this is word zero, word one, word two, and word three, and then I have a key here. Okay, so how would this matching happen? Well, very simple. Recall in earlier lecture we studied the equality comparator. So basically, what we do, we take the bits. Suppose this key is 4 bits from bit 3 to 0, and every word of those has 4 bits as well. Okay, so what we do, we take this key and match the key with every bit of the key with every word. Key 3 with the word 0 bit 3. Key bit 2 with word 0 bit 2, etc. until key bit 0 with word 0 bit 0. So this here I am matching the key with word 0, and here I match the key with word 1, and here I match the key with word 2, and here I match the key with word 3. And basically what I'm using here is the equality comparator. Okay, basically XNOR gates followed by an AND gate. So that match line tells me if this match line is 1, it means what? It means that the key is equal to what? The key is equal to word 0. If match 1 is 1, it means the key is equal to word 1, etc., etc. Okay, so that matching tells me where the matching happens, right? Did match? Is the key matching? Is the key matching word 0 or word 1 or word 2 or word 3? Now notice that any one of this could be a 1. Okay, so if suppose I don't have a match here, this is no matching, 0 0 0 0. Then this 0 detector tells me if miss equals 1, it means I do not have the key in my memory. So this is what the miss signal tells me. Okay, If no of all the match lines, so this is a 0 detect circuit. If all the match lines are zeros, then the miss equals 1. So now we go to the transistor. Now, how I can match the key bit one single bit with the value in the word. So this is one bit. This is one bit in one of those. So this is, let's say, bit I in word 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 J. Okay, so this is bit I in word J, and now this is what, this is the key. I place the key. This is key bit I. So I send these bits of the key to to these bit lines, right? And what happened? I implement here the X OR. Okay, now you will tell me, wait, but we are using here XNORs, right? Right? Yeah, oh yeah, but we will do bubble logic here, so that we can save inverters. So we will use it XOR. Okay, so this is an XOR here. So notice that here this cell prime, this value is cell prime, and this is here cell. All right, and here you the bit, and this is bit prime. Typical XOR. Okay, so we will discharge this line if there is a mismatch. If there is a match, we will not discharge it. Okay, all right, so now what we have here, you will see this is these are the cells here that I showed you a second ago, and these are the more clearly here, more sort of zooming in. So suppose I have a key of 1010, and suppose the value of the first word 1010, and the value of the second word 1111, and the value of the third word 0000, and the fourth and the fourth word 0000. And in this case, we will see that there is a match at 0. The match 0 goes 1. Why? Because the key matches word 0. Okay, the key matches word 0. In other words, you'll see this line that is pre-charged. I will not discharge this line in any of the cells. I will not discharge, and therefore it stays high. Okay, notice that here match is 0 because the key is not equal to the word. Match is 0, match is 0. And eventually, because of that, the miss equals 0 because I found a match. Whoops, this keeps changing on me. I found a match, which is right here. Okay, so the miss equal to 0. Okay, so hopefully the circuit shows you how this is activated. If this match, for instance, if this match was, let me see, for example, if this match, oops, sorry, if this match here is 0, then this miss line will be a 1. Now, of course, obviously the data has to reflect that there is a mismatch. Okay, so now hopefully now you can appreciate what we are doing, which is the XORing to evaluate these match lines, and then the miss. Okay, so now oops, this thing is making me really okay. So now what we can say is the following. Is that now, okay, let's see. Let's see if I can get my pen here back. Now, if I have a memory here of, let's say, for example, physical page number, I have a hit for the virtual page, for example. Okay. Now I need to access the very first word because I will get my physical page number. The physical page number is not in location 1, is not in location 2, is not in location 3, it's rather in location 0 because I matched the virtual page number in the location 0. Okay, with that I conclude my okay, so let's see here. This is the match. The matching circuit is dynamic circuit because of this clock, and the miss circuit is is a pseudo inmass, and all that for speed and consideration and size consideration. Okay, so for the matching, what we do, we leave the word line low, we pre-charge these match lines, okay, which are because they are dynamic circuits, and then we place the key on the bit lines, and the match evaluates within the cells. Okay, so the missed line, which is this one here, it is a pseudo inmass. Okay, and basically, if all these inmasses are off, then the output goes high. Okay, I think I said all what I want to say for the cam, and thank you very much.